On August 6, 2025, the James Webb Space Telescope fixed its gaze on something traveling through our solar system and captured the sharpest, most chemically detailed image of an interstellar comet ever produced by human beings. Not a fuzzy dot, not an unclear smudge of light. A complete spectral portrait, a reading of the chemistry of an object from another star system, delivered in the infrared wavelengths that Webb was specifically designed to detect, spanning the range from 0.6 to 5.3 micrometers, where the molecular signatures of the universe's most important compounds are hidden in frequencies that ground-based telescopes and even Hubble simply cannot reach. What that image revealed was something the scientists who received it described using a word that isn't used lightly in peer-reviewed planetary science: extreme. The chemistry of 3I Atlas, the third confirmed interstellar object ever detected passing through our solar system, was described in the Nature paper published June 22, 2026, as producing findings that surprised the researchers. Not findings that confirmed expectations, but findings that surprised scientists who had spent months preparing the observation, running the spectral analysis, and checking the data repeatedly before submitting to Nature, because the numbers fell so far outside the range of anything ever measured in any solar system comet. This video covers what Webb actually discovered, why the chemistry of this ancient visitor is driving a genuine rethink of what protoplanetary disks look like around other stars, and why the multi-observatory campaign surrounding 3I Atlas throughout the second half of 2025 and into 2026 represents the most comprehensive scientific engagement with an interstellar object in history. Subscribe right now before this video ends, and hit the notification bell because the 3I Atlas story isn't over. The comet is leaving the solar system, but the papers are still coming out, the data is still being processed, and the next major result could shift the picture again. To understand what Webb found and why it was surprising, you first need to understand what 3I Atlas is, and how rare an opportunity it was to study it. Interstellar objects, bodies that originate outside our solar system, form around another star, and are then ejected into interstellar space to drift through the galaxy, were purely theoretical until 2017. Astronomers had long argued, on statistical grounds, that interstellar space should be full of them. When solar systems form, not all the material involved ends up incorporated into planets. Comets and planetesimals in the outer disk get gravitationally scattered by giant planets, and a significant portion are flung outward on trajectories that exceed the escape velocity of their parent star system entirely. They become free-floating bodies drifting through the galaxy at whatever speed the ejection gave them, carrying the chemical signature of the environment where they formed. For decades, this population stayed invisible to us. These objects are dark, cold, and moving through a vastness of space so empty that any given cubic astronomical unit is essentially nothing. The only time they become visible is when one happens to pass through another star system, close enough to the star to heat up, sublimate volatiles, grow a coma and tail of gas and dust that scatters light and becomes detectable by telescope surveys. In 2017, the Pan-STARRS telescope in Hawaii detected the first confirmed interstellar object ever, 1I Oumuamua. It was already headed outward when found, moving too fast to intercept, and showed no coma or tail despite active efforts to find one. Its odd, elongated shape and unexplained non-gravitational acceleration sparked significant scientific debate that remains unresolved. In 2019, 2I Borisov was discovered, a clearly comet-like interstellar visitor with an active coma, the first interstellar comet confirmed beyond doubt. Borisov's chemistry was studied extensively and found broadly consistent with solar system comets, though with some differences. Then, on July 1, 2025, the Atlas Survey Telescope in Chile detected 3I Atlas moving at roughly 250,000 km/h relative to the Sun on a hyperbolic trajectory, the mathematical signature of an object that didn't form in our solar system and isn't gravitationally bound to it. It was already actively outgassing at a distance from the Sun, where most solar system comets remain dormant. This was the third interstellar object in recorded history, and by far the most chemically accessible, arriving close enough and at the right time of year for Webb, Hubble, and a fleet of other observatories to study it in detail before, during, and after its closest approach to the Sun in late October 2025. David Jewett of UCLA, who confirmed the comet's interstellar nature using the Nordic Optical Telescope within days of its discovery, described it plainly, clearly active, growing a coma from the moment it became detectable. Unlike Oumuamua, which showed no activity and more chemically evolved than Borisov, 3I Atlas was from the start a chemically rich target. The Webb observation on August 6, 2025 used the near-infrared spectrograph NER-SPEC, to capture a spectral image of 3I Atlas when the comet was roughly 272 million kilometers from Earth and about 3.3 astronomical units from the Sun, the distance at which Jupiter orbits. At that range, most solar system comets are only just starting to show signs of activity, still too cold for water ice to sublimate efficiently from the nucleus surface. Yet 3I Atlas was already producing a substantial coma. The Webb spectrograph spread the comet's light across a range of wavelengths and measured precisely which ones were being absorbed or emitted, producing a chemical fingerprint as distinctive as a barcode, identifying which molecular species were present in the coma and in what relative amounts. This is the same transmission spectroscopy technique Webb has used to characterize exoplanet atmospheres, now applied to a body moving through our own solar system at interstellar speeds. What the spectrum revealed, once processed by the team at NASA's Goddard Space Flight Center led by Martin Cordner, was a coma dominated by carbon dioxide rather than water, the same molecule that makes dry ice, a compound that sublimates at much lower temperatures than water ice and is therefore active much farther from the sun. The ratio of carbon dioxide to water in 3I Atlas's coma was roughly 8 times higher than in any previously measured solar system comet. 8 times, not a marginal difference. Among solar system comets studied in detail over decades, the range of carbon dioxide to water ratios varies, but a value 8 times above the previous maximum is a step change, not a variation. It means the relative abundance of these two compounds in 3I Atlas is so different from anything formed in our solar system that it points directly to formation under fundamentally different conditions. The full molecular inventory Webb detected in the coma included water vapor, carbon monoxide, water ice, dust, and trace compounds including carbonyl sulfide. Each of these species sublimates at a specific temperature, corresponding to a specific distance from a star, which in turn corresponds to a specific region within a protoplanetary disk. The proportions in which they appear are a direct record of where in that disk, and under what temperature conditions, the material that became 3I Atlas originally condensed. The carbon dioxide dominance says something specific about that origin. In protoplanetary disks, different volatile compounds condense out of the gas at different distances from the central star, a series of frost lines, each marking the boundary inside of which a given compound is too warm to remain as ice, and outside of which it can condense. Carbon dioxide condenses at a frost line much farther from the star than water does. A comet, formed mainly from carbon dioxide ice, formed in the cold outer reaches of its protoplanetary disk, far from its parent star, under conditions unlike those in which the water ice-dominated comets of our own solar system formed. The Nature paper, led by Cordner, put these numbers into their precise scientific context. The methane-to-water ratio in 3I Atlas was roughly 11 times higher than in any previously measured solar system object. The deuterium-to-hydrogen ratio in the detected water was about 30 times higher than in solar system comets. Both measurements, combined with the carbon dioxide dominance, pointed toward the same conclusion: a formation environment far colder and situated at a specific point in galactic chemical evolution, unlike anything that produced the comets of our own Oort cloud and Kuiper belt. The age implications of these measurements are where the story becomes genuinely remarkable. Age-velocity dispersion is a well-established relationship in galactic astronomy. The older a stellar population, the faster its individual stars tend to move relative to the local standard of rest, the average motion of stars in the solar neighborhood. Over billions of years, gravitational interactions with molecular clouds, spiral arms, and other mass concentrations gradually scatter stars in velocity space, widening the range and increasing the average magnitude of their motions. By measuring an object's velocity relative to the local standard of rest, astronomers can produce a statistical estimate of its likely age. 3I Atlas was moving at more than 200,000 km/h, roughly 2.2 times the speed of 2I Borisov. Astrid Taylor at the University of Michigan, studying the velocity-age relationship for 3I Atlas, put its age at somewhere between 3 and 11 billion years. Chemical analysis led by Cordner, examining the carbon isotope ratios in the coma, pushed that estimate further to between 10 and 12 billion years. Our solar system is 4.6 billion years old. Our sun hasn't yet reached the midpoint of its expected lifespan. 3I Atlas formed between 10 and 12 billion years ago, when the universe was roughly 1.8 to 3.8 billion years old, far younger than its current age of about 13.8 billion years. The star it formed around, wherever it was located in the Milky Way, has almost certainly completed its life cycle and died in the billions of years since the comet was ejected from its home system. Matthew Hopkins and his team at the Center for Astronomy and Astrophysics at the Technical University of Berlin traced 3I Atlas's trajectory backward, using the Gaia satellite's catalog of nearly 2 billion stars, reconstructing the comet's path through the galaxy to its arrival in our solar system. Their analysis pointed to the thick disk of the Milky Way as its region of origin, an older, kinematically distinct population of stars spread further above and below the galactic plane than the thin disk where our sun resides. The thick disk is dominated by stars more than 10 billion years old, with chemical compositions reflecting the galaxy's early chemistry before generations of stellar nucleosynthesis enriched the interstellar medium with the heavier elements common today. This places 3I Atlas's origin in a genuinely ancient region of the galaxy, consistent with all the chemical evidence in the Webb spectrum. A comet formed around an old, metal-poor star in the galactic thick disk, in a protoplanetary disk whose chemistry differed from our own because the star itself formed from material that predated most of the heavy element enrichment that had occurred by the time our sun formed 4.6 billion years ago. The Webb observation was only one piece of what became the most comprehensive multi-observatory campaign ever conducted on an interstellar object. Alongside the gas chemistry in the coma, Hubble's ultraviolet and visible light capabilities supply detailed structural information about the dust component. Hubble's images revealed the overall dust morphology of the coma, a distinctive distribution pattern around the nucleus that offered insight into dust grain sizes, mass loss rates, and the geometry of the tail as it began developing under increasing solar radiation pressure. Together, the two instruments gave scientists something they'd never had for an interstellar object before: a complete portrait. Webb reading the gas chemistry, Hubble mapping the dust structure, both datasets describing the same object simultaneously from complementary angles, building a picture of 3I Atlas's physical and chemical properties, in more detail than any previous interstellar visitor had allowed. JWST's X-RISM X-ray satellite contributed an observation in late November 2025 that achieved something no instrument had ever managed before with an interstellar object. It detected X-ray emission from 3I Atlas. Neither 1I Oumuamua nor 2I Borisov had produced any detectable X-ray emission despite observational attempts during their passages. For 3I Atlas, X-RISM's detection confirmed an extensive gas cloud surrounding the nucleus, extending roughly 400,000 km from its surface. An X-ray halo generated by the interaction between the outgassing coma material and the charged particles of the solar wind, a process known as charge exchange. The scale of the halo, larger than the average distance between Earth and the Moon, big enough to fit every planet in the solar system side by side, confirmed that 3I Atlas's outgassing was genuinely extraordinary compared to its predecessors. NASA's SPHERE-X mission captured the comet in late December 2025, as 3I Atlas began its outbound journey after perihelion. The observations showed the comet, in the words of SPHERE-X scientists, fully erupting, a dramatic surge in activity as the sun's heat finally penetrated the nucleus's insulating outer layers and reached the deep interior ice that had been preserved for billions of years in interstellar cold. Water emission rose by a factor of 40 above baseline in the weeks following perihelion, driven by delayed thermal penetration finally reaching the water, ice-rich interior layers that had been shielded during earlier stages of the solar approach. The comet's rotation changed measurably during this outburst. Before perihelion, its rotation period was 16.2 hours. Afterward, as jets of escaping gas exerted torque on the spinning nucleus, rotation sped up to 7.1 hours, more than twice as fast. This spin-up matched models of how asymmetric outgassing drives rotational change and confirmed that the outgassing wasn't uniform across the surface, but concentrated in specific active regions functioning like small rocket engines, gradually accelerating the nucleus as the outburst intensified. One of the most precisely determined physical parameters of 3I Atlas emerged from a geometric coincidence in early 2026. On January 22, 2026, 3I Atlas passed within 0.699 degree of the Earth-Sun axis, the imaginary line running directly from Earth, through the Sun's center. This solar opposition geometry placed the Sun almost directly behind the observer relative to the comet, eliminating the shadows normally cast by dust particles in the coma and producing a temporary, roughly 20% brightness enhancement through constructive interference of reflected sunlight. The Hubble Space Telescope used this brightness boost to accomplish something it hadn't managed precisely during its August 2025 observations, isolating the nucleus from the surrounding coma clearly enough to measure its size directly. The result? 3I Atlas has a nucleus radius of approximately 1.3 kilometers, a diameter of roughly 2.6 kilometers. At the lower end of the range, earlier estimates had suggested, and consistent with a nucleus active across a large portion of its surface, meaning the modest overall size combined with the extraordinary outgassing rates implies that most of the nucleus is contributing volatile material rather than just isolated active patches. That same opposition event also revealed the structure of 3I Atlas's jets in extraordinary detail. By using filters to remove the symmetric glow of the surrounding coma, the Hubble team identified 4 distinct jets emanating from the nucleus, 1 prominent sunward jet that had been tracked for months, and 3 smaller jets spaced at roughly 120-degree intervals around the sunward axis. The near-perfect symmetry of these 3 smaller jets drew significant attention, with the 120-degree spacing too precise to be easily dismissed as random. The most plausible explanation is that these 3 mini-jets originate from compositionally or structurally distinct regions of the nucleus, positioned at those angular intervals relative to the rotation axis, geological structure reflecting how the nucleus assembled within its protoplanetary disk billions of years ago. On March 16, 2026, 3I Atlas passed within 0.358 astronomical units of Jupiter, approximately 53.6 million kilometers, placing it inside Jupiter's Hill sphere, the region where the planet's gravity outweighs the sun's influence on passing objects. The gravitational deflection from this encounter was estimated at just a few meters per second of velocity change, tiny in absolute terms, but meaningful when extrapolated across cosmological timescales. This was almost certainly the most significant gravitational interaction 3I Atlas has experienced since the ejection event that originally launched it out of its parent star system, potentially billions of years ago. The Europa Clipper spacecraft, currently en route to Jupiter's moon Europa to investigate the potential habitability of the ocean beneath its ice, was diverted from its cruise phase operations on November 6, 2025, and spent 8 hours continuously imaging 3I Atlas. Reprogrammed mid-mission to observe an interstellar comet no one knew was coming when the mission launched. The returned UV images confirmed the presence of hydrogen and oxygen in the coma, the telltale chemical markers of water ice sublimation, and picked up faint dust structures in the developing tail. ESA's JWST spacecraft, the Jupiter Icy Moons Explorer, observed 3I Atlas on the same date from a distance of 66 million kilometers, capturing 120 images using 5 of its instruments. Because JWST was using its main high-gain antenna as a heat shield at the time, data transmission was limited to its smaller backup antenna, so the full set of JWST observations didn't reach Earth until February 2026. Among the data that arrived was video, a sequence of 53 images from JWST's navigation camera showing 3I Atlas moving through space with its coma and twin tails visible. Navigation cameras aren't built for science, they're designed to track star positions for spacecraft orientation. This was a case of being in the right place at the right time, yielding something the instrument was never meant to provide. By the time 3I Atlas rounded the sun and began its outbound journey, roughly 500 papers and studies had been published about this single interstellar visitor. The scientific output, over about a year of observation, substantially exceeded what had been produced for 1I Oumuamua and 2I Borisov combined. Part of the reason is that 3I Atlas was simply more accessible, arriving at an angle in time that allowed extended observation across many months. Part of the reason is that the observational infrastructure available in 2025 and 2026 was simply far more capable than what existed during the 2017 and 2019 passages. Webb didn't even exist during Oumuamua's passage. And the infrared spectral portrait Webb produced of 3I Atlas in August 2025 would have been impossible with the telescopes available 8 years earlier. And part of the reason is that 3I Atlas turned out to be more chemically interesting than either of its predecessors, in ways the 500 papers have only begun to fully explore. The methane-to-water ratio, 11 times higher than any solar system object. The deuterium-to-hydrogen ratio, 30 times higher than solar system comets. The carbon dioxide dominance, 8 times beyond the maximum ever measured in a solar system comet. The first X-ray detection of any interstellar object. The first detailed infrared spectrum of an interstellar comet's coma. The first size measurement of 3I Atlas's nucleus. The first confirmed that was Cassini and Enceladus. But the direction of the 3I Atlas findings matches what Cordner's team concluded in the Nature paper. The chemistry of this object isn't just quantitatively different from solar system comets, it's qualitatively different, in ways that point to an origin around a different type of star, in a different chemical environment, at a fundamentally different epoch in the galaxy's history. Every major chemical measurement, the CO2-to-water ratio, the methane-to-water ratio, the deuterium-to-hydrogen ratio, the carbon isotope signature, produces a number that falls outside the range established by the entire population of solar system comets studied over decades. No single one of those measurements alone would be conclusive. Taken together, they all point in the same direction, toward the same conclusion. An ancient, cold origin around an old star in the galactic thick disk. That is the Nature paper published on June 22, 2026. What does 3I Atlas actually mean for our understanding of the universe? It means we now have real chemical measurements from a real object confirming that the range of protoplanetary disk chemistry found around other stars is genuinely wider than our solar system alone could ever reveal. Our own comets, the chemical leftovers of our solar system's formation, are a sample from one data point. 3I Atlas is a sample from a different one. Its chemistry describes an environment we can now partly reconstruct from the spectral data Webb returned. Colder, richer in carbon dioxide, richer in methane, more enriched in deuterium, formed around a star whose disk had a different composition than the disk around our young sun 4.6 billion years ago. The galaxy is chemically diverse. Protoplanetary disks around other stars don't all resemble ours. The comets those disks produce don't all carry the same volatile inventory. And when those comets are ejected and travel through the galaxy for billions of years before passing through our neighborhood, they carry that chemical diversity with them. A message from a distant system, readable by the right instrument, if that instrument arrives in time to capture it. James Webb arrived in time. The observation on August 6, 2025, produced a data set that will be analyzed for years to come. The papers building on it are still being published. The comparison between 3I Atlas's chemistry and the chemistry predicted by models of thick disk protoplanetary disks remains an active area of research. And when the next interstellar object arrives, 4I, whatever it turns out to be, the lessons of 3I Atlas will shape how quickly observations are mounted, which instruments get pointed at it, and what questions get asked first. The Vera Rubin Observatory is now fully operational, scanning the entire southern sky every few nights, with an instrument so sensitive that it had already picked up 3I Atlas in its science validation data 10 days before the official discovery date. The next interstellar comet will be found earlier, observed longer, and studied using everything 3I Atlas taught us about what to look for and why it matters. Subscribe and hit the notification bell right now if you haven't already. The 3I Atlas papers are still arriving from the teams that observed its solar passage. JWST data is still being processed. The full analysis of the December 2025 outburst is still being completed. Every major result to come out of this extraordinary ancient visitor will be covered here with the same sourced, accurate approach you just heard. 3I Atlas came from 10 billion years away. It carried chemistry we had never measured before, and for 1 year, it let the most powerful telescope humanity has ever placed in space read what was inside it. What Webb found was surprising, and science at its best is exactly that.